Okay, is it on? Okay, so the symbol of the Dolbeau operator. I'll just state the answer. It's well, it's pretty straightforward to deduce it from the answer for the de Rham operator. Okay, so what is W? W, well, W is an element of lambda p of Tx tensor lambda q of Tx. And what is psi 0, 1? Well, psi 0, 1 is the following thing. We have psi, and psi lives here. Now, okay, let me write psi here. So psi goes to psi tensor 1. And then I decompose this as the 0, 1 as the 1, 0 component plus 0, 1 component, and forget the the 1, 0 component. And what remains is the 0, 1 component. Basically we take an element here and wedge it by an element inside Tx of x, and we get an element inside the component p q plus 1. So we have seen two differential operators, the de Rham operator and the Dolbeau operator, and these are closely related. And we have calculated the symbol of one, and well, the symbol of the other is pretty straightforward from the first one. Now let's define elliptic operators. This seminar is supposed to be about elliptic operators. Now, what are these? A differential operator is elliptic, if and only if. If its symbol, same remark applies as half an hour ago. every operator has some order. When we talk about the symbol, we by default we mean the symbol of the same order as the order of the operator, because all other symbols are either not defined or are identically zero, and as such they aren't very interesting. Symbol. Well, the symbol is a map of vector bundles. And we require that this map should be an isomorphism on the tangent bundle of X minus the zero section. What does this mean? Well, let's recall that the symbol depends on psi. And we want that for every psi non-zero, the map which we have should be an isomorphism. Well, none of the operators we've seen today so far is elliptic. Later on we'll see how to construct an elliptic operator starting from the de Rham operator. The de Rham operator in itself is not elliptic, but if we take the de Rham operator plus the adjoint operator, we get an elliptic operator. The same is true for the Dolbeau operator. The de Rham operator is not elliptic, but it's not very hard to construct an elliptic one starting from it, and we'll see it in well, either next time or the one after it. Anyhow, let's give at least one example of an elliptic operator, which is basically which is a very particular case of another example, namely the one which I've just mentioned. Starting from the de Rham operator, one can construct an elliptic operator. How? Take the de Rham plus the adjoint. Then one can square it. One can square the result, and one gets the Laplace operator. And here is, and we'll talk about it in more detail. It's a very important operator. But before we do, let's consider a very simple example of the Laplace operator. Okay, let's take x equal R2 and let's take the trivial bundle on R2 of rank 1. So the sections of the trivial bundle are the same as functions on R2. Well, as you probably have seen, many times. There's the Laplace operator, which is given as the sum of the second derivatives with respect to x and y, and it's probably familiar. And by the way, just by looking at this expression, one of the things that come to the mind of a physicist is how to take the square root. This is how Paul Dirac invented the Dirac operator, which will be very important for us in the sequel. So normally, well, if you just take this expression, it doesn't make sense to consider the well, to try to find the square root of this. It looks hopeless, but if one uses Clifford algebras, this question becomes more meaningful, and in the end, what one gets is the Dirac operator, which is quite important for topology, and maybe physics too. But let's not talk about it. Well, not. Anyway. A very simple example, and one can check by hand that this operator is indeed elliptic. By the way, what will the symbol be? Well, the symbol depends on two things, on x and the cotangent vector. And it must be a map from R to R. So it's a number. What is this? What is this number? Yes, psi 1 squared plus psi 2 squared, okay. Let's write it down. It's clear from this expression that this thing doesn't vanish except when psi is 0. And later on, we'll see how to generalize this example to an arbitrary Riemannian manifold. Okay. Now, now we know what an elliptic operator is. Now, every elliptic operator is Fredholm. We'll prove this. It is important that M is compact. If M is not compact, this is not true at all. For example, d by dx on R is elliptic, but it's definitely not Fredholm. Now, what is Fredholm? Does everyone know? Well, just to to remind everyone. Well, every operator has kernel and co-kernel. The Fredholm condition says that the dimension of the kernel is finite, and so is the dimension of the kernel. Well, let's recall that the spaces this operator acts on spaces of sections, and the result of applying the operator is again to a section is again a section. Okay. Now the index. What is the index? The index of D. Okay, let me write it properly. It's basically the one of the main objects. The index is the dimension of the kernel minus the dimension of the co-kernel. Okay, now here V and W are just vector spaces, not necessarily finite dimensional. Well, let's do a couple of examples. For example, what's the index of what's the index of an operator from a finite dimensional space to itself? Well, it's an exercise in linear algebra to prove that the index is actually 0. On the other hand, if we take, for example, the space L2, there are operators which have any given integer index. Can someone give me an example? Where L2 is L2 on n. Okay, left shift. What will the index be if we take L2 of n and shift to the left?
Kernel is one-dimensional.
Yes.
Is,
yes. So the left shift, one place to the left, has index 1. And similarly, the right shift has index -1, and so on. Does this make any sense? L2 of n is the space of all sequences A0, A1, A2, such that the sum of the sum of the squares of those numbers is finite. Well, here L2 is not very important. Instead of L2, we could take basically L1 or L infinity, or even the direct product of n copies of R, because here we are interested in just vector spaces. Now, the left shift takes a sequence like this one and shifts it one place to the left, and which means the shifted sequence starts with A1 and then A2 and so on, and A0 vanishes. And this is why we get a one-dimensional kernel. On the other hand, the co-kernel is zero-dimensional. So we get 1 minus 0, which is 1. Okay. It makes sense to consider the index for linear maps between infinite dimensional spaces. Okay, now now we want to calculate the index of an elliptic operator. So suppose we have D from C infinity E to C infinity F, elliptic, and we want to calculate the index. Well, well, the first piece of good news is that in order to calculate the index, we only need to know the symbol. Now, the symbol gives me an isomorphism of between Well, an isomorphism okay. To be quite honest, I need to restrict everything to the spherization of the cotangent bundle. Now, what's the spherization? I just take the cotangent bundle, introduce some metric, and take the bundle of the unit spheres. So this thing stands for spherization. Well, instead of a vector bundle, I just consider the bundle of the corresponding sphere bundle. Okay, so this is an isomorphism. Now, as we will see, and it's not very difficult to see this. Such an isomorphism gives me an element which I denote by the same symbol, and which lives in K in the K theory with compact support of T upper star of X, or, which is the same, the reduced K theory of the Thom space of T upper star of X. Now, let's see whether or not we understand all the words. Now, does the word K theory with compact support make any sense? No. Okay. So, okay. Does the Thom space make any sense? Okay. So let's start with the Thom spaces. There are several. Again, there are several ways to define the Thom space. The easiest one is suppose we have a vector bundle. This time, let's take a real vector bundle, which means in particular it could be a complex vector bundle. Let me introduce a metric. Well, X is not necessarily a manifold. What I mean is that I have a symmetric, positive, definite bilinear form on each fiber, and this form varies continuously with the element of the base. In particular, if X is a Riemannian manifold, we can take this symmetric bilinear form to be the Riemannian metric, but we don't have to. We could take just any other family of Euclidean metrics on each fiber separately, but we need them to vary continuously with the fiber. Okay, then the Thom space of V is dV by S of V, where d of V is the unit disk bundle and S of V is the unit sphere bundle. Okay, does this make sense? Well, this means we have the unit disk bundle, and inside it we have the unit sphere bundle, and then we collapse the unit sphere bundle. Есть такая важная операция в топологии. Значит, пространство под пространство, значит, можно схлопнуть под пространство. Не, все вместе. We collapse all of the unit sphere bundle to a single point. Yes, well, it's a topological space. Yes. By the way, suppose I have something and nothing. What happens if I take something and collapse nothing?
I know what is collapsing. I'm trying to understand what kind of object is top space.
Well, it's something which knows a lot about the neighborhood of the zero section.
So it is just
and doesn't know much about what happens far away from the zero section.
Настройка пространства тома тривиального равновесия,
Is it worth to mention that it's the one-point computation of bundle? I mean,
yes. Well, if X is compact, then what we get is the same as the one-point compactification. Anyway, so the Thom space. And by the way, well, we read it. Let's say the Thom isomorphism. Is everyone familiar with the Thom isomorphism?
I think not.
Okay, so suppose E is orientable. Then orientable in the usual sense, which means every fiber has an orientation, and the orientation depends continuously on the point of the base over which we take the fiber. Then there is an isomorphism okay. I will write diagonally, but hopefully this doesn't lead to any kind of confusion. Okay. Okay. So here we have the homology of X. And here we have the reduced homology of the Thom space. And here we have the cup product by the Tom class. Okay, am I right that those people who were asking about the Tom class just left? Okay, is everyone, are all people who are remaining familiar with the Tom isomorphism? No. Okay. So, the homology of X and the reduced homology of the Tom space. Okay. Now, what is U? U U is basically an element of okay, let me to make it clearer where this comes from. Let me also write the reduced homology of the Tom space as the homology or cohomology of the unit disk bundle modulo the homology of the unit sphere bundle. Okay, now well, R is the rank of E. And U is the Tom class. What I want to say here is that if E is orientable, then there exists a class U, and moreover a unique class U, such that copying by U induces an isomorphism from the cohomology of X to the cohomology of the Tom space, which we identify with the cohomology of the disk bundle modulo the sphere bundle. Now, does this make any sense? Is everyone familiar with the cup product? If not, let's talk about it. Значит, видели ли вы такую штуку, как значит, кап произведение двух классов? Значит, ну, еще у нас бывает относительная гомология, точнее когомология. И в них тоже определено кап произведение. Значит, в чем его смысл? Значит, мы можем взять класс значит, когомологии по модулю чего-то, еще один класс когомологии по модулю чего-то еще. Потом перемножили, получили класс по модулю объединения. Yes, if we take two relative cohomology classes, one class mod something, another class mod something else, we cup them, and the result is another cohomology class mod the union of the somethings. Okay, now here I have the cohomology of X, but I am allowed to replace it with the cohomology of the disk bundle. The disk bundle is homotype equivalent to X. Okay, now I have a class here, the disk bundle mod sphere bundle. When I take a class here, couple it with a class here, I get another class. I get another class in the relative cohomology disk bundle modulo the sphere bundle. Okay, and the Thom isomorphism theorem says that if E is orientable, then we have this this isomorphism. Okay, now another remark which we'll need is that there is the Thom isomorphism theorem for compactly supported cohomology as well. Now, does this expression make any sense? Compactly supported cohomology. Okay. Now, there are several ways to define the compactly supported cohomology. Let's конечно. Ну, такой философский вопрос. Но я бы сказал, что так ощутимо. Ну, значит, в буквальном смысле, нет, но там женщин нет. Там D от E это многообразие с границей. Ну, соответственно, его граница это S от E. Если X многообразие. Значит, у нас есть двойственность Пуанкаре Левшица для многообразия с границей. Ну, то есть в буквальном смысле нету, но в каком-то смысле есть. Okay, so let's see how much time we have left. Well, we have another half an hour. Okay, so compactly supported cohomology. Okay, again, let's give a simple definition, which is not the most general one, but at least it's quick. Suppose I have suppose I have a finite CW pair, and I want to define the compactly supported cohomology of the difference. Now I simply declare it to be equal the relative cohomology X mod Y. Okay, and by the way, now if we know what K theory is, we know what we also know how to define K theory with compact support. Namely, suppose we have this T upper star of X, we represent it as something as a finite CW complex minus a subcomplex, and then take the relative K theory. So same recipe. Works for K theory. Okay, so we know now we know what the Thom space is, and we know how to define K theory with compact support if we know how to define K theory. K theory is a sort of a cohomology theory which is constructed using using vector bundles. Let me. I don't want to define K theory today because I want to do it justice. And so K theory is a sort of a cohomology theory, and we'll talk about it in more detail, which has all the properties of the usual singular homology except one. The K theory of a point is not concentrated in degree 0. Instead, it's it is equal z in all even degrees and 0 in all odd degrees. So it's the K theory of a point is more complicated than the cohomology of a point.
Вот когда мне теория получается, что то есть это там группа.
К-теория – это функтор из там, CW пар в градуированное векторное пространство или там, градуированные группы, которая удовлетворяет там, всем аксиомам Хильденберга-Маклейна, кроме той, которая говорит, что для точки у нас там, гомология сосредоточена или там, когомология сосредоточена в одной размерности. It's a cohomology theory, which is in a sense the simplest cohomology theory, which does not come from the usual singular cohomology. And there are things which are hard to detect using using K theory, and conversely, there are things which are easier to detect using K theory than using ordinary homology or cohomology. And there are many more homology and cohomology theories, and we'll probably need to talk about those at some point because we need K theory. But let's just postpone this this part because, as I said, let's do it justice. So K theory is some kind of cohomology theory, which sort of resembles the usual homology, but not quite. And starting from this geometric construction, namely an isomorphism of two vector bundles, which are defined on T upper star of x, and which are isomorphic on the spherization. Starting from this geometric data, one can construct an element of the relative, of the compactly supported K theory of the Thom space, and we'll talk about that. Now, there is another thing we will need, and it's the following one. Suppose we have x where x goes to y, a proper embedding of smooth manifolds. Now, I want to define a map, a push-forward map for compactly supported K-theory. No. Okay, so I lower shriek I want to define a map I lower shriek from the compactly supported K-theory of X to the compactly supported K-theory of Y. Well, let's just remember this this expression, compactly supported K-theory. So far, it may sound mysterious, but we'll talk about it in more detail later on. And in some way, this is not much more difficult than compactly supported cohomology or relative cohomology. Okay, so. What do? Well, let's assume that the normal bundle has a complex structure. Then we have the I shriek map, which is as follows. First, we take we go from the K-theory of X to the K-theory of the Thom space via the Thom isomorphism, and then let me take Y. Y contains a small neighborhood of X. Let me collapse the boundary of the small neighborhood. What will I get? I will get the Thom space. So in cohomology or in K-theory, I get a map. So on the level of spaces, I have a map from here to the Thom space, and on the level of K-theory, I have a map in the opposite direction. I take the composite, and this is the map I lower shriek. Where is it all going? We want to state the Index Theorem. And we have 20 more minutes to do this. Okay, yes?
Вот КЦ это получается контравариантный функтор, правильно?
Контравариантный относительно собственных отображений и ковариантный относительно открытых вложений. А вот точно так же с когомологией с компактным носителем, правильно? Вот у нас, если что-то открытое, то они отображаются в прямую сторону, а если собственное отображение, то в обратную.
Но вот эта стрелка
Да.
Она получается как раз из...
Нет, стрелка снизу вверх — это изоморфизм Тома. В смысле, вот эта стрелка сверху вниз.
Нет, снизу вверх.
А снизу вверх — это открытое вложение. Вот смотрите, у нас нормально... сейчас, извините, да, yes, you're absolutely right. This is, I have to use either the Tom space or compactly supported cohomology, but not both. Okay, yes, thanks. That's a good remark. So let me use compactly supported K theory. And in this case, I just have the normal bundle, which is embedded in Y as an open subset, and I take the the induced map of compactly supported K theory.
Вот это и с восклицательным знаком. Это как раз из контрвариантности получается, или это другое что-то?
Значит, и с восклицательным знаком это...
Нет, в другую сторону.
Ну, здесь, да, значит, здесь у нас есть одна, которая ковариантная, другая, которая изоморфизм Тома. Значит, в общем, это что-то вроде экстраординарного пулбека. Вот, значит, некоторые люди возвышенные называют его интегрированием постоянно. Но, значит, дело вот в чем. Вот пусть у вас есть два многообразия. Ну, значит, в когомологиях можно пойти из... Значит, просто из таргета в source обычным pullback'ом. А можно пойти в обратную сторону. Можно в таргете применить двойственность Пуанкаре, потом push-forward, потом двойственность Пуанкаре. Значит, вот это аналог для этих самых, для К-теории. И он работает, значит, потому что расслоение нормально, в смысле, потому что нормальное расслоение имеет комплексную структуру, или там более общо, то же самое работает для вещественных расслоений, не обязательно комплексных, значит, на которых существует спинция структура. Значит, мы потом про это поговорим. Okay. Again, we'll talk about this later. I want to state the index theorem before the time runs out. But yes, we will definitely need to talk about this later, because well, for those who haven't seen it, this all may sound mysterious. Yes, so now I think we have all ingredients. I think now we have all ingredients. So the index theorem. So suppose we have a smooth compact manifold, an elliptic operator. From the sections of E to the sections of F, E and F are smooth complex vector bundles, and I want to calculate the index of D. Well, to do this, let me embed x in Rn.
Is it closed maybe?
Yes, let me take, well, x is compact, so every embedding is automatically closed. Okay, I embed x in Rn. Then I embed the, well, this gives me an embedding of the tangent bundle in the tangent bundle. And the same for cotangent bundles. Now, the normal bundle of the normal bundle of this inside this has a complex structure. Well, which is basically because the normal bundle is just a direct sum of two copies of the tangent bundle pulled back to itself. Well, no. Here we have a normal bundle, and here we also have a normal bundle. Well, this normal bundle is isomorphic to the direct sum of two copies of this one pulled back to x, which is not particularly tricky. The benefit is I lower shriek is defined. Now the index theorem. What does it say? Well, it says the following thing. I take I lower shriek of this element, and my claim is that this is the index. Well, let's see why this makes sense. The index is a number, and what is this? Well, this thing, by definition, is inside compactly supported K-theory of T Rn. Well, this is the same as this is the same as the reduced K-theory of S to N, which by the Bott theorem is isomorphic to Z. And the claim is that if we combine if we apply this isomorphism to this element, what we get is precisely the index. Now we have a simple formula for the index, which which only uses the element sigma d in square brackets, which is constructed from sigma d, and sigma d is the symbol. So the index only depends on the symbol. Unfortunately, this formula involves K-theory. There is a way to rephrase the formula using cohomology. At least if the manifold is orientable. We have 7 minutes left. Now the question is, do we have enough strength left to see another version of the index theorem? Okay. Yes. Okay. Let's do this. Okay. I will draw some diagram, and basically the idea is there is a map from K-theory to cohomology, which forgets everything about torsion, but which is still useful for our purposes, namely the Choyan character. Okay, so what do we have? We have K-theory with compact support of TRN. Yeah, cohomology basically I want to I've erased it already. Basically I want to go through the definition of this map. As n, normal. Okay. It's not particularly. Okay. So what is y? Y is not the same. Okay, no, let me put a z here because y is not the same as the other y. So what is z? Z is a tubular neighborhood of z is a tubular neighborhood of Tx inside Rn. And this is a vector bundle over X. which is compact. So well, if I like, I can keep the C, and or I could erase the C. It doesn't matter. Okay, now let's okay. Now let me. Now let me. Let me put the Tn, Tx here. Okay, so Z is a neighborhood. A neighborhood of what? A neighborhood of Tx inside Trn. So the base is anyway. Here we have Tx, which is the space, the neighborhood of which we take. Okay, so we have this diagram. Let's see. Let's call this. Bundle nu. So here we have the Thom isomorphism for nu. Nu is the normal bundle of this inside this. It has a complex structure. So it makes sense to consider the Thom isomorphism. Well, it also makes sense to consider the Thom isomorphism here. Well, if a bundle is this bundle, as we know, has a complex structure. Well, if it has a complex structure, it's certainly orientable with respect to the usual cohomology theory, and so the Thom isomorphism makes sense. Okay, now let's look at this diagram. Does this diagram make any sense whatsoever? Well, not yet. Anyway, why not? Because we don't know what this arrow is. Well, this is the Chern character. This is the Chern character. We'll talk about the Chern character. Don't worry. And here. Unfortunately, we have something more complicated than the Chern character.
Why do I say it's actually easier than character? Because it's like much closer to the mark.
Say again? Let's talk about this later. Okay, so so here we need to twist the Chern character by the Todd class. The Todd class of what? The Todd class of nu. But nu is the normal bundle. It has a complex structure, so it makes sense to times elements of this group by the Todd class of nu. So again, what does this map do? It takes an element here, takes the Chern character. The Chern character is an element here. Now we can times elements of the compactly supported cohomology by elements of the usual cohomology. Well, the Todd class of nu is an element of the usual cohomology of Tx, and I take the Chern character, times it by the Todd class. We don't know what the Todd class is any more than we know about the Chern character, but we'll talk about both. Okay, now I have this map. I have this map, and basically I want to reduce the question to some calculations in cohomology and not in K-theory. Cohomology is, well, maybe it's more familiar to many people than K-theory. So this is Tom. Well, to be quite honest, we have this arrow only if x is orientable in the usual sense. Another version is this. The index of D is Tom to the minus 1 of the Chern character Tom to the minus 1 of the Chern character of sigma D times, or cob, the Todd class of nu the Todd class of nu x tensor C. Now we know, sort of know, everything in here except this, and this is the stable normal bundle. Which means the normal bundle of any embedding of x in a sufficiently high-dimensional Euclidean space. Okay. Now, this formula is basically a consequence of this formula and the diagram. And we also need the fact that the Tom isomorphism. So this always true is if x is orientable in the usual sense. So the Tom class is linear with respect to multiplication by the cohomology of x. So yes, so the Tom isomorphism is linear with respect to the cohomology of the base. So which is why we're able to take this out of this bracket. And what remains is the term to the -1 of the Chern character applied to the to some element of K-theory which is obtained from the symbol. And this is basically the formula which we will use for all applications that we will see. The de Rham operator, the Dolbeau operator, the signature operator, the Dirac operator, basically all applications we'll cover in this course will follow this strategy. Normally we know this sigma d or square sigma d in square brackets more or less explicitly, and then we use tricks of various types to calculate the CH and then apply term to the -1. And so this is basically this is it. Well, you have there you have it. Well, it's just one version of the index theorem. There are several more versions, more general and so on. But already this one is quite useful. Okay, I think I've run over time again. Sorry about that. Anyway, are there any questions? There aren't.
В следующий раз как бы сильно медленнее будет.
Значит, нет, в следующий раз мы начнем, наверное, сначала. Но там сегодня была такая мотивирующая часть. Значит, в следующий раз мы начнем говорить про, более подробно про операторы такие-сякие, там и значит, в общем, нужно подумать, что хочет публика. Например, значит, публика хочет скорее узнать про анализ или скорее узнать про К-теорию или то и другое. А если то и другое, то в каком порядке? В общем, мой план был, в следующий раз рассказать про операторы, вот с точки зрения там анализа и геометрии чуть подробнее, посмотреть на Дирам там и там понять, понять, что такое там Лапласиан и почему его индекс равен тому, чему он равен. Равен он Эйлеровой характеристике. В общем, я думаю, что здесь нужно спросить публику, что думает публика. Так, публика устала. Хорошо. Значит, неудивительно, Денис, значит, уже знает топологическое, хочет аналитическое. Ну хорошо. Значит, так, слушайте, давайте мы сейчас выключим запись.